Welcome students. As a continuation of second law of thermodynamics, now we'll see what is a Carnot engine. Carnot engine is an heat engine. It is pronounced as Carnot. Okay, T is silent here. Now this is a ideal engine. Okay, I'll assume I'll take some ideal gas in a cylindrical vessel whose sides are made up of adiabatic material or insulating material. Piston is also made up of insulating material only. The bottom only is conductor. Okay, perfect conductor. As I told you, a heat engine works between two different temperatures. One should be a high temperature source and the other one should be a low temperature sink. So I'll take a source here at higher temperature T1 and a sink here at lower temperature T2, and there is one adiabatic stand also. Okay, right? Initially the gas, I'll take gas which is at a pressure P1, volume V1, and initially temperature T1 equal to that of the source. Okay, right? So I'll represent that in the PV diagram by the point A. Here the pressure is P1, okay, volume is V1, and temperature is T1. Okay, now what do? I'll put this cylindrical vessel on this source such that the bottom of the vessel will come into contact with the heat source here. Now the first step is, right, I'll allow the gas to expand, right, the gas to continuously take heat from the source at high temperature when you are and isothermally. Okay, means temperature should not increase. So what will happen? In order to keep the temperature constant, right, the volume of the gas will keep on increasing, temperature remains constant, right, pressure and volume, pressure will be slightly decreasing, volume will be increasing. Okay, it takes Q1 amount of heat and allow Q1 amount of heat. It's very slowly, right, we keep on feeding it some Q1 amount of heat such that its temperature remains constant, pressure and volume may change. Okay, so the first step in Carnot engine is what is known as an isothermal expansion. Okay, isothermal expansion from the point A, which is at P1, V1, T1, to a point called B where pressure is P2, volume is V2, but temperature remains as T1 because the process is isothermal. At a constant temperature T1, the system keeps on absorbing energy from the source, Q1 amount of heat energy, and keeps on expanding. Okay, gas is pushing the piston up means what? Gas is doing some work. Okay, what type of work it is? Isothermal. Okay, when a process work done, right, an isothermal process is what? W1 equal to, right, nRT. The temperature of the source is T1. At constant temperature T1 we are doing this. nRT1 log final volume by initial volume. Final volume is V2 by initial volume is V1. So the work done in the first step is nRT1 log V2 by V1. That I'll call it as W1. Okay, next, when gas, so from A it will go to a point B. Okay, it goes to a point B where pressure is P2, volume is V2, but temperature remains as T1 only. Okay, in isothermal process we have seen in first law of thermodynamics, all the heat given will be converted into work. Okay, what is the work done by the gas? It is given by the area between this curve and the volume axis. This entire area, right, will give you the work done by the gas in this process. Okay, next step is, once I go to B, right, I'll change this vessel onto this adiabatic stand. So now what will happen? Already sides are adiabatic, upper part is also in adiabatic condition. Now bottom also becomes what you call an insulating stand here. Okay, such that now the system is totally under adiabatic conditions. Heat cannot go into system or come out of system, but I'll allow the gas to expand without giving any heat. Earlier the expansion was by giving some heat Q1. Now this process is taking place in adiabatic conditions. Okay, right, there is no heat going on system, but I'll allow the gas to expand. When the gas is allowed to expand without giving any heat, right, what is happening? Gas is pushing the piston up. Where from the gas is getting energy to push the piston up? Okay, it will spend its own internal energy. Okay, means internal energy is decreasing means temperature is decreasing. Okay, I'll allow the gas to expand till its temperature falls down from T1 to our sink temperature T2. Okay, that is second step. That I'll call it that process is known as adiabatic expansion. Okay, in adiabatic expansion, that is step 2. Okay, step 2, it is adiabatic expansion. Adiabatic expansion from the point B, which is at pressure P2, volume V2, temperature T1, to another point C where the pressure is P3, volume is V3, but temperature now decreases to T2. Okay, we can represent that in the PV diagram like this. In an PV diagram we have seen, right, the slope of the adiabatic is gamma times more than the slope of the isothermal. Means the adiabatic curve will be steeper than the isothermal curve. It will be like this. Okay, now by the time the gas comes to this new point C where pressure is P3, volume is V3, temperature T2, right, volume is increasing but pressure keeps on decreasing drastically. Okay, because the temperature keeps on falling down in adiabatic expansion, pressure also decreases drastically. The pressure becomes so low, the gas will lose its ability to do work. Okay, even if I try to allow it to expand, the pressure becomes so low that gas cannot push the piston up. So I have to stop that process here. Okay, at a point C, predestined point C, I'll stop the process. Okay. Right, so system goes to point C. Now again I'll transfer this vessel from this adiabatic stand on to the sink now. Now what should happen? The engine should come back to its initial stage. Okay, it is like this. I cannot continuously keep on expanding the gas and keep on getting what you call work from the gas. No, it is not possible practically. Why? In isothermal process, all the heat given will be converted into work, right? You are giving heat to the gas is pushing the piston up, you are getting work. But how long this process can continue? Okay, how long can we allow the gas to expand? We need to have that much big vessel, isn't it? Okay, and after some time what happens when the gas is pushing the piston up and up? Of course we are initially getting work, but sometime what will happen? Pressure becomes so low that the work done PdV, okay, pressure becomes extremely small, the gas will lose its ability to do work. Okay. After some time what should we have? What should we do? You have to bring the gas back to its initial point, right? By doing some work on it, such that some net work is done by that gas and it becomes a cyclic process. Okay, means that's why all engines work in cyclic process. They will take the system, okay, from one point to another point, they'll extract some work. By doing lesser amount of work, they'll bring the system back to its initial point such that I'll get some net work in the process. So that's why all engines work in cyclic process only. Now the volume has become so big, okay, and pressure has become so small, gas has lost its ability. Now we should bring it back to what you call the initial point. How should I bring it back such that I get net work done? Maximum net work is done by the gas, not on the gas. Okay, means if I take the system back like this, okay, work done by the gas is less, work done on the gas is more. Okay, so it is loss for us actually. I am looking for net work done from the gas. Okay, means I should take it back to here. Means if I take it exactly in the path it has come, what will happen? Work done by the gas is equal to work done on the gas. Net work done is 0. It is waste of time, no use. Okay, in what way I should take the system back? I should take the system back with minimum amount of work like this, as minimum as possible. If I take it like this much is the amount of work done by the gas, whereas work done on the gas is only this small amount, such that I'll get some net work done. Okay, work done by the gas is more, work done on the gas is extremely small, such that net work is done by the gas. That is our profit in running this cyclic process. Okay, right, means I should go like this as slowly as possible and still take the system back to its initial point, such that the system is ready to do work now. Again, just like we put petrol in a bike. Okay, I put 1 liter petrol, I go for 50 kilometers. If I keep on going like that, what will happen? Okay, after 50 kilometers, the bike will stop. What should I do in order for the bike to run continuously? After every, right, 50 kilometers, 45 kilometers only, I should stop the bike, right? I should put some petrol, and again I can go forward like that. Means we have to keep on feeding it back. Or I am riding on a horse, say. Horse is initially energetic. I take the horse for 50 kilometers. If I don't feed it, what will happen? The horse will die after some time. So what should I do? Right, I have to stop going. Okay, stop riding the horse, give some food, give some rest to it. Again tomorrow I should start, so that again the horse is ready, right, to do extra work. Okay, same is the case with engines also. Okay, by the time engine has come to this point, it has lost its ability to do work. Now it is my duty to take it back to its initial state, just like feeding the horse and giving it some rest. Okay, right, now again I'll draw this figure. Okay, it is like this. Pressure, volume, PV diagram. Okay, starting from A, it went to B. From B, it went to C. Okay, right? This is isothermal expansion. This is adiabatic expansion. Now what do? I'll transfer this vessel from this adiabatic stand onto the sink. And now the gas is also at temperature T2 only. Sink is also at temperature T2. Now what do? Gas has expanded to the maximum possible value. Now I'll start pushing the piston down. I will start doing work on the gas. Okay, right? I'll slowly keep on pushing the piston such that the heat of compression will not allow the temperature of the gas to increase, but that heat of compression gets rejected into the sink. Okay, right? I'll keep on pushing the piston down. Whatever is the amount of work done will get converted into heat, and that heat is pushed into the piston, pushed into the sink like this, such that temperature of the gas remains at T2 only. Okay, means what type of compression it is? Isothermal compression at a lower temperature T2. Okay, that is isothermal compression. Volume is decreasing. Okay, pressure will slowly increase to, I'll push the piston up such that it goes to a point D where the pressure is P4, volume is V4, temperature is T2. Temperature is T2. Okay, so here pressure is P1, V1, T1. Here it is P2, V2, T1. Here it is P3, V3, T2. Here it is P4, V4, T2. This is an isothermal compression. Okay, next what happens? I have to increase the temperature from T2 to T1. Okay, increase the temperature from T2 to T1 means again I'll transfer this vessel onto the adiabatic stand. Now I'll again start pushing the piston down. Okay, now what happens? Whatever work I'm doing will get converted into heat, but there is no chance for that heat to escape, right? Because everything is under insulated conditions. So what will happen? Temperature of the gas will keep on increasing. Okay, I'll compress the gas till its temperature comes back to T1. Okay, adiabatic curve is represented like this. Okay, now the system goes back to initial volume, initial pressure and initial temperature. One cycle is completed. Okay, this is known as Carnot cycle. Okay, Carnot cycle we call. Okay, it's a 4-stroke engine. Okay, 1 stroke, second one, third one, fourth one. Okay, 4-stroke engine it is, right? So it is the first engine to be perceived by a French scientist called, French engineer called Carnot. Okay, right? This is an ideal engine because we are taking that it is an ideal gas, ideal source, ideal sink, ideal adiabatic conditions, ideal conductor, everything is ideal here. Okay, but still, even its efficiency should be less than 1 because second law of thermodynamics, right, says what? No engine can have efficiency equal to, forget about greater than 1, no engine can have efficiency equal to 1 also. So our Carnot engine, however ideal it may be, its efficiency also will be less than 1 only. That we'll see now. Okay, now what is the work done on the gas? What is the work done on the gas means area between this curve and this curve, and volume axis means this entire area is the work done on the gas, work done by the gas. What is the work done on the gas? Work done on the gas will be like this. Okay, work done on the gas is this area. It is this area. What is the net work done? This area minus this area, it is nothing but this one. Okay, this is the net work done by the gas. Net work done by the gas or on the gas. Work done by the gas is more, net work done. Work done on the gas is less, so net work is done by the gas only, given by this entire area. Means the area of the Carnot cycle in a PV diagram gives what? It is net work done. Net work done. Okay, and the cycle is clockwise, so the area enclosed by clockwise circle gives you net work done by the system or by the gas. Okay, now what is this second step? Second step is isothermal expansion, right, for which the work done, adiabatic expansion, for which the work done, the formula is step 2. It is like this. W1 we have already seen, isothermal expansion. Now the W2 is adiabatic expansion. Okay, adiabatic expansion W2 is equal to NR by gamma minus 1 into T1 minus T2. T1 minus T2. This is the expression for work done in that adiabatic process from B P2 V2 T1 to C P3 V3 T2. Okay, the third step is what is known as isothermal compression between C and D. Okay, the third step is isothermal compression. Isothermal compression from C P3 V3 T2 to D P4 V4 T2. Process isothermal process, temperature remains same. What is the work done in isothermal process again? Okay, what W3 equal to, okay, NR, at what temperature this compression is taking place? At a lower temperature T2, nRT T2 log final volume by initial volume. What is final volume? Final volume is, right, V4, initial volume is V3 in this compression. So it is V4 by V3. Okay, V4 by V3 to the base E. Okay, now which one is bigger, volume V4 or V3? If you look at the graph, okay, V3 is here, V4 is here at this point D. At this point D, V4 is there. V4 is less than V3. Okay, right? Now here, log smaller quantity by bigger quantity, it's a negative one. So we can directly write this as, I can take that negative sign common and write this as what? Minus nRT2 log, right, V3 by V4 to the base E. This is work done negative because log smaller quantity by bigger quantity will be negative. So I have taken negative common and writing this as V3 by V4. Okay. Now the fourth step is adiabatic compression. Adiabatic compression from D to A. From D to A. The fourth step is adiabatic compression from that point D where pressure is P4, volume is V4, temperature is T2 to it's the initial position A where pressure is P1, volume is V1, temperature is T1. What is the work done in adiabatic process? Right? Work done W4 equal to, right, NR by gamma minus 1 into initial temperature minus final temperature. Initial temperature, the gas is initial at lower temperature T2. Finally, we are taking it to T1. So that is T2 minus T1. T2 minus T1. Okay. T2 is less than T1. So T2 minus T1 will be negative. So I will take that minus sign common. Minus NR by gamma minus 1 into T1 minus T2. I'll write. Okay. Right, so there are 4 steps, and 4 steps 4 different works are done: W1, W2, W3 and W4. What is the total amount of work done or net amount of work done? Positive, you take it as positive, negative, you take it as negative. We'll directly get the net work. Okay, the net work done is like this. Okay, W equal to W1 plus W2 plus W3 plus W4. What is W1? NR T1 log V2 by V1 to the base E. What is W2? W2 is work done in adiabatic expansion. In adiabatic expansion, work done is NR by gamma minus 1 into T1 minus T2. What is W3? W3 is minus nRT2 log V3 by V4. Okay, therefore, W3 is minus NR by gamma minus 1. Sorry, it is isothermal process, isn't it? So, minus nRT2 log V3 by V4. V3 by V4. What is the fourth step work done? Minus NR by gamma minus 1 into T1 minus T2. Okay. Here we have plus nr by gamma minus 1 T1 minus T2. Here we have minus nr by gamma minus 1 T1 minus T2. So this and this, they get cancelled. So the net work done W will be due to this W1 and W3 only. W1 is nr T1 log V2 by V1 minus, okay, W3 is nr T2 log V3 by V4. This is expression for the net work done in a Carnot cycle. Okay, what is efficiency? How do you define efficiency of any heat engine? Efficiency of any heat engine is defined as work output by heat input. So efficiency eta equal to W by what is the input we are giving? Q1. Okay, now what is the first step in an isothermal process? First law of thermodynamics says what? dq equal to du plus dw. Okay, in an isothermal process internal energy remains constant, so du is equal to 0. So in an isothermal process dq is always equal to dw. So whatever work we are getting, nr T1 log V2 by V1 will be equal to the amount of heat Q1 which it has absorbed. Okay, means Q1 is also equal to W1 equal to nr T1 log V2 by V1 to the base E. Okay, so that is nothing but this whole thing is the net work done by Q1. This is our efficiency expression eta, means by, I'll write the same as nr T1 log V2 by V1 to the base E. Okay, nr, they get cancelled. Okay, what remains is the efficiency expression is eta equal to, okay, eta equal to, right, T1 log V2 by V1 to the base E minus T2 log V3 by V4 to the base E by, right, T1 log V2 by V1 to the base E. Okay, this is expression for the final eta. Okay, right, sometimes in MS entrances question will come, the expression for the efficiency of a Carnot engine, he'll give this term fully, T1 log V2 by V1, okay, minus T2 log V3 by V4, or sometimes they'll give plus T2 log V4 by V3. Be careful, okay, whether V3 by V4 means it is minus sign, if it is V4 by V3 it will be plus sign only here, by T1 log V2 by, same term should come here. Okay, try to remember this. Next, now we'll go to, we'll use some thermodynamic relations, what we know. In that PV diagram, what we have drawn, okay, this is an adiabatic process, B to C. B to C is an adiabatic process. Here temperature is T1, volume is V2. Okay, here temperature is T2, volume is V3. Okay, and DI is also an adiabatic. Here temperature is T2, volume is V4. Here temperature is T1, volume is V1. From B to C, it's an adiabatic process, right? What is the relation between temperature and volume in an adiabatic process, right? What is the relation between temperature and volume? We should recollect that it is TV to the power gamma minus 1 equal to constant. Means here temperature is T1. So T1 V2 to the power gamma minus 1, because here volume is V2, is equal to, right, what is temperature here? T2, right? V3 to the power gamma minus 1. So, right, V2 by V3 to the power gamma minus 1, V2 by V3 to the power gamma minus 1 equal to T2 by T1 we can write. Okay, similarly in this adiabatic DA also, right, the temperature volume relation is what? What is temperature here? T2. What is volume here? V4. T2 V4 to the power gamma minus 1 equal to T1 V1 to the power gamma minus 1, or, right, T2 by T1 equal to V1 by V4 to the power gamma minus 1. So from this adiabatic we got this relation for T2 by T1. From this adiabatic we got this relation for T2 by T1. So now we equate these two. This is also T2 by T1. This is also T2 by T1, isn't it? So equate this V2 by V3 to the power gamma minus 1 equal to V1 by V4 to the power gamma minus 1 implies what? Okay, V2 by V3 equal to V2 by V3 equal to V1 by V4. V1 by V4. Remember this, V2 by V3 equal to V1 by V4, or V2 by V1 equal to V3 by V4. So in Carnot cycle, V2 by V1 is equal to V3 by V4. Okay. Now come back to our earlier expression, the final expression what we have got for the efficiency here. Okay. Right. Here we have V2 by V1. Here we have V3 by V4. Just now we have proved that V2 by V1 equal to V3 by V4. Means V2 by log V2 by V1, V3 by V4 is also equal to V2 by V1. So this gets cancelled, this gets cancelled, and this gets cancelled. Okay, what remains is simply eta equal to, right, T1 minus T2 by T1, or 1 minus T2 by T1. Okay, eta equal to. Okay, so the final expression for the efficiency of a Carnot engine in terms of the absolute temperatures of source and sink is, right, eta equal to 1 minus T2 by T1. What is the most general expression for efficiency of any car, any heat engine? For any heat engine, in the last video we have seen the expression for energy is eta equal to the expression for energy is eta equal to, right, Q1 minus Q2 by Q1. Okay, now we have got here for a Carnot engine T1 minus T2 by T1. See, this is a Carnot engine. Okay, only for a Carnot engine it is T1 minus T2 by T1, not for all heat engines. Okay, right? Why? Because we have taken, how did I get T1 minus T2 by T1? Because we have cancelled V2 by V1 as equal to V3 by V4. How could I cancel V2 by V1 with V3 by V4? Because it is a reversible adiabatic process. Okay, reversible adiabatic process between B and C. Okay, similarly between D and A also it is a reversible adiabatic process. Only in a reversible adiabatic process those relations PV to the power gamma, right, TV to the power gamma minus 1 equal to constant are valid, not for any irreversible process. Okay, so Carnot engine, right, all the 4 steps in Carnot engine are reversible isothermal expansion, reversible adiabatic expansion, reversible isothermal compression, and reversible adiabatic compression. Okay, because they are all, it's a reversible process, we got T1 minus T2 by T1. So T1 minus T2 by T1 is only for a reversible engine. Okay, for any other engine or an irreversible engine it is Q1 minus Q2 by Q1. For a Carnot engine this is general expression for any engine. For reversible engine it is equal to this. So I am equating these two. When we equate these two, what do we get? Q1 minus Q2 by Q1 equal to T1 minus T2 by T1 means eta equal to, okay, 1 minus Q2 by Q1 is equal to 1 minus T2 by T1. Therefore, in a Carnot cycle, Q2 by, right, Q1 is equal to T2 by T1. Very important relation. Okay, which has given rise to many important consequences also. Okay, this is the final expression for the efficiency of a Carnot engine is 1 minus Q2 by Q1, 1 minus T2 by T1. See, 1 minus T2 by T1 is only for a Carnot engine, which is a reversible engine. Okay, in general it is 1 minus Q2 by Q1. Okay, right? Now, we'll see some problems in this and what are the consequences of this result also, we'll see now. Okay, now, so we have got the expression for efficiency of a Carnot engine as 1 minus Q2 by Q1 is equal to 1 minus T2 by T1. Okay. Right, this is one expression for efficiency. Now I'll define one more parameter called adiabatic expansion ratio rho. What is adiabatic expansion ratio? The ratio of volumes in an adiabatic process. Okay, the BC is an adiabatic, we have seen. Final volume V3 is greater than the initial volume V2. So V3 by V2, okay, right, is known as adiabatic expansion ratio. Similarly, this is an adiabatic compression here. In an adiabatic compression, what is happening? Volume is changing from decreasing from V4 to V1. So here volume is more, Okay, here volume is less. So V4 by V1 is also known as adiabatic expansion ratio. So V3 by V2 equal to V4 by V1 equal to rho. Rho is known as adiabatic expansion ratio. Now in this adiabatic, we have seen T1 V2 to the power gamma minus 1 equal to T2 V3 to the power gamma minus 1, or V2 by V3, that's what we have earlier written, V2 by V3 to the power gamma minus 1 equal to T2 by T1. Okay, this we got equal to, okay, V1 by V4 to the power gamma minus 1, that's what earlier we have written. Okay, now what is V2 by V3? V3 by V2 is rho. So what is V2 by V3? 1 by rho. So this is 1 by rho to the power gamma minus 1 equal to T2 by T1. Okay, that is same for V1 by V4 also. So either V2 by V3 or V1 by V4, it is 1 by rho to the power gamma minus 1. So in the expression for efficiency eta, right, it is 1 minus T2 by T1. T2 by T1 is nothing but 1 by rho to the power gamma minus 1, that is 1 minus 1 by rho to the power gamma minus 1. Okay, this is also one way of putting the efficiency of a Carnot engine in terms of adiabatic expansion ratio. Okay, so look at this result. This is a very crucial result what we have got, the efficiency of a Carnot engine. So what can we conclude? Okay, from this result, 1 minus for any engine, 1 minus Q2 by Q1. Especially for a reversible Carnot engine is a reversible engine. Efficiency is 1 minus T2 by T1. So from these two expressions, we can conclude that, right, Q2 by Q1 equal to T2 by T1, or Q2 by T2 equal to Q1 by T1. Okay. These two are very, very useful, okay, from exam point of view in solving problems and from concept point of view also. Okay, right, now what do we conclude from this? The efficiency of a Carnot engine depends only on the source and the sink temperatures of source and sink, that's all. It is independent of the nature of the working material. Okay, what type of gas you are taking is immaterial. No working substance is not coming into picture. Okay, so efficiency of a Carnot engine, that is the first most important conclusion, is what? Efficiency of a Carnot engine does not depend on the nature of the working substance. That is first point. Okay, second point is, right, it is independent of the area enclosed by the PV diagram for the Carnot cycle. Okay, whatever may be the area, means you draw a smaller PV diagram or a bigger PV diagram. Okay, in a bigger PV diagram, area enclosed is more, work done is more, but still efficiency is independent of area of the PV diagram. Because it depends only on the temperatures of source and sink. So, right, the efficiency of a Carnot engine, for the first point is depends only on the temperatures of source and sink. The second point is it is independent of nature of the working substance. The third point is it is independent of the area of the PV diagram in what you call area of the Carnot cycle in PV diagram. Okay, then we may get it out, sir, bigger area means bigger work, smaller Carnot cycle means smaller work, isn't it? When work is more, efficiency should be more. Okay, the expression for efficiency is eta equal to, basic expression for efficiency is, right, eta equal to W by Q1. Okay, right, work output by heat input. You take one Carnot cycle like this. Okay, right, this Carnot cycle A, B, C, D. Here temperature is T1. Here temperature is T2. Okay, now it is having some area, its efficiency eta equal to W by Q1. What have we seen now? Efficiency of a Carnot engine is independent of the area of the PV diagram. Okay, area of the Carnot cycle in the PV diagram. Okay, you take a bigger, bigger Carnot cycle like this. From B, extend it to B dash, right? The extend it to C dash. Means A, B dash, C dash, right? D. A is a bigger Carnot cycle. A, B, C, D is a smaller Carnot cycle. This one's area is double that of the first one's area, but still both have same efficiency. Why? Here temperature is T1, here temperature is T2. No sir, area is bigger. Okay, work done is more, so efficiency should be more. No, when work is more, this for smaller area, okay, it is taking lesser Q1. W is less. Okay, net work done is less. Heat taken as what you call input also will be less. Okay, from A to B it takes Q1 amount of heat only. In order to go from A to B dash, it will take another Q1. Okay, work is also getting doubled and heat input is also getting doubled. It is like this. I eat 1 plate idli and walk for 5 kilometers. You eat 2 plate idli and walk for 10 kilometers. Efficiency is same. Okay, for plate idli we are running or walking 5 kilometers. Okay, right? So bigger area means work done is more, but Q1 also will be more. Smaller area means work done will be less, Q1 also will be less. Okay, so area of a Carnot cycle is independent of the efficiency of a Carnot cycle is independent of the area of the Carnot cycle in the PV diagram. Now we can draw this PV diagram, right, clearly like this. Okay, this process A to B, it is extracting Q1 amount of heat. Okay, here pressure is P1, V1, T1. Here it is P2, V2, T1. Okay, here it is P3, V3, T2. Okay, here it is P4, V4, T2. Isn't it? In going from A to B, reversible isothermal expansion, system is absorbing Q1 amount of heat and it is converting all that Q1 into work. Okay, B to C, no extraction, it is an adiabatic process. C to D, it is isothermal compression. We are doing work on the system. Okay, whatever work we are doing is getting lost as heat into Q2 into the sink. Means system is taking Q1 amount of heat in this step. System is losing Q2 amount of heat into the sink in the third step like this. Okay. Right? Now, this area enclosed by the Carnot cycle will give you the net work done. Okay, but efficiency depends only on initial temperature and final temperature. Okay, sorry, sink temperatures of source and sink. Also, we have got Q1 by T1 equal to, okay, Q1 by T1 equal to Q2 by T2. This is in a reversible Carnot cycle, Q1 by T1 equal to Q2 by T2. This is another important result. Okay, this has led Lord Kelvin, okay, to define a new temperature scale itself. Okay, what he has observed is in a Carnot cycle, right, the ratio of two temperatures is equal to ratio of heats absorbed and rejected by Carnot cycle at those temperatures. What is Q1? Q1 is the amount of heat absorbed by the Carnot engine at temperature T1. What is Q2? Q2 is the amount of heat rejected by the Carnot engine at temperature T2. The ratio of two temperatures, right, is equal to ratio of heat absorbed and rejected by Carnot engine at those temperatures. This has given the hint for Lord Kelvin to define a new temperature scale. He has defined what is called absolute scale. He has defined what is known as absolute scale of temperature, okay, based on this concept. Okay, how did he define absolute scale? In that scale, ratio of any two temperatures in his new absolute scale or Kelvin scale or work scale, thermodynamic scale, it has many names. Okay, the ratio of any two temperatures theta 1 and theta 2 in that scale will be equal to the ratio of heats absorbed and rejected by a reversible Carnot engine working between those two temperatures. Means take what you call two temperatures, theta 1, theta 2. Okay, you make one Carnot engine operate between these two temperatures. See what is the amount of heat extracted, Q1 at that temperature. Okay, and rejected heat, Q2 at this temperature. That ratio Q1 and Q2 you measure, that ratio is equal to ratio of these two temperatures, he said. Means ratio of two temperatures in absolute scale is equal to the ratio of heats absorbed and rejected by a reversible Carnot engine between those two temperatures. Okay, that's how he has defined the Kelvin or thermodynamic scale of temperature. Okay, and coincidentally, okay, what has been observed is This thermodynamic temperatures measured in thermodynamic scale are equal to the temperatures measured in ideal gas scale. Okay, in ideal gas scale means temperatures measured by a constant volume hydrogen gas thermometer. Okay, they are found to be identical. Means the ratio of two temperatures in thermodynamic scale, theta 1 by theta 2, are found to be, this ratio is found to be equal to those of an ideal gas scale. Ideal gas temperatures are denoted by T1 and T2. So thermodynamic scale temperatures or Kelvin scale temperatures are also denoted by T1 by T2 from there onwards. Okay, right? So capital T1, capital T2 is a general notation used in thermodynamic scale or Kelvin scale. What he did is, he has taken the triple point temperature of water, okay, triple point temperature of water as a standard one. Okay, right? What is triple point temperature of water? It is 0.01 degrees Celsius. Okay, he called this 0.01 degrees Celsius as equal to 273.16 Kelvin. Okay, 273.16 Kelvin is equal to the triple point temperature of water, 0.01 degrees Celsius. So what will be 0 degrees Celsius? 0 degrees Celsius will be 273.15 Kelvin. So what is 0 Kelvin? 0 Kelvin will be minus 273.15 degrees Celsius. Okay, 0 Kelvin. See, for Celsius we'll put a small circle here, degrees Celsius, but for temperature in Kelvin scale we should not put 0 degrees Kelvin. Okay, we should not write this, right? Simply 0 Kelvin, that's all. Okay, so 0 Kelvin is equal to absolute zero temperature, we call. Okay, the lowest temperature possible in the universe, absolute zero temperature. Okay, right? In degrees Celsius is minus 273.15 degrees Celsius. Okay, right? Usually people, we neglect this 15 and we say T degrees Celsius plus 273. We ignore this 0.15, write it as absolute scale. Means 27 degrees Celsius means we'll simply add 273 to it and call it as 300 Kelvin. Okay, in thermodynamics all temperatures must be taken in Kelvin scale only. All temperatures must be taken in Kelvin scale. Even sometimes if degrees Celsius is given, add 273 and convert to Kelvin scale. Okay, right? This is how Kelvin has defined absolute scale or Kelvin scale of temperatures, in which 0 Kelvin, absolute zero temperature, is minus 273.15 degrees Celsius. Okay, and there is, we are talking about second law of thermodynamics. There is one more law called third law of thermodynamics. Okay, that is unattainability statement of third law of thermodynamics. Says what? In a finite number of operations it is impossible to reach absolute zero temperature. Means nobody can reach this temperature. Okay, minus 273.15 degrees Celsius cannot be reached. That is a law in thermodynamics. Okay, now when somebody says it is impossible, what do scientists do? They keep on trying to poke their nose into that only. So now the aim of man is what? Try to reach absolute zero. Though absolute zero, reaching absolute zero is not possible. Okay, go as close as possible to absolute zero. Okay, means if not minus 273.15 or 0 Kelvin, okay, people are reaching now to 0.000000000 like that. Now we have about pico-Kelvin temperatures, okay, femto-Kelvin temperature, 10 to the power, nano-Kelvin temperatures have come in 2000s only. Now people are going to 10 to the power minus 12, 10 to the power minus 14 Kelvin, like that. As close as possible to absolute zero. Okay, right? New mechanisms are getting invented to reach lower and lower temperatures. Okay, up to 1975, the lowest temperature reached was only about 0.0014 Kelvin, that's all. Okay, now we are going into nano Kelvin, 0.901, 1001, 1201, like that. Okay, right? So this is about absolute scale. All temperatures measured in thermodynamics should be in Kelvin scale only, right? So we will solve some problems in Carnot cycle in the next video and proceed to the concept of entropy, okay, in the next video itself. Now at the end of the video, from the next video onwards, right, I'll take up one thermodynamics problem, okay, which has appeared in previous jam questions, and solve that. Okay, one jam question, irrespective of the topic, let it be thermodynamics or any topic, one good previous year question, okay, problem will be solved after the end of the lecture in every video. So please watch the video till the end, okay, such that many previous year problems, they can be from jam or gate or CSR, right? Depending on the depth of the problem, it will be solved. Thank you.